In this video, we're going to cover galvanic cells, and I'm going to explain it in a way to try to give you a deep, intuitive understanding of them. But to develop that understanding, you have to have a great understanding of direct redox reactions. So the first half of this video is actually going to be about direct redox reactions, and then the second half will be connecting that to how galvanic cells work. Direct redox reactions occur when two chemicals are in the same vicinity, and one chemical transfers an electron or multiple electrons directly to the other chemical. To understand these, you need to have a good understanding of reduction potentials. And what reduction potentials tell us is how much a chemical, which will be represented on the left side of the reaction arrow, how much that chemical wants to gain electrons. And they will give you a value that tells you that. And the unit for that value is volts. You can also think of it as how much does the chemical on the product side want to hold on to those electrons. We can then use the reduction potential for two chemicals to see, can one of these chemicals take electrons from the other? So we have a situation here where we have silver ions in solution, and they are in direct contact with this copper metal strip. And then we are given the reduction potential for both copper ions and silver ions. Since we're dealing with solid copper instead of copper ions, you want to be asking yourself, can this solid copper hold on to its electrons? So you're not asking yourself, can this copper gain more electrons? The silver is present in its ion form, so for that one you are asking, can this silver gain new electrons? So the copper is holding on to those electrons with a value of 0.34, and the silver wants to take those electrons with a value of 0.8. Since the 0.8 is larger, the silver ions will be able to take electrons from that solid copper. And when you're dealing with redox reactions, you want to be thinking a lot about half reactions. Our reduction half reaction is silver ion gaining an electron to become solid silver. The oxidation half reaction is solid copper losing 2 electrons to become the ionic copper plus 2 electrons. So for the oxidation half reaction, make sure those electrons are on the product side. And I'm not going to get into balancing redox reactions, but our final redox reaction would be 2 silver ions plus 1 solid copper results in the production of 2 solid silver plus 1 copper ion. And then the picture on the right side shows us the result of that, which is the accumulation of solid silver on the bottom of that metal copper strip. And then instead of having silver ions in solution, we now have copper ions in solution. And if we had more silver ions in solution, we would have more buildup of silver on that copper strip, and more of that copper strip would dissolve into the solution. And one final note about reduction potentials, because I've seen a lot of people get confused about this. When you look at the half reactions for these reduction potentials, don't think of these as the actual reactions that are occurring. Those are just values that have been determined in a laboratory, and then we're able to use them to evaluate if a reaction will occur. And we saw that with the copper half reaction, where the copper was not actually in its ionic form, but we just used that reduction potential to tell us if silver could take electrons from that solid copper. Now we're going to use the concepts from the direct redox reaction to explain galvanic cells. In a galvanic cell, we're basically taking the same situation and separating it into 2 different beakers. On the left side, we have the solid copper metal, and on the right side, we have those silver ions. And the same thing is basically going to happen where the silver ions are going to take electrons from the solid copper, but this time those electrons are going to have to travel through a wire to get to the silver ions. So we put a solid strip into the solution with the silver ions, and this solid strip could be silver or it could just be a different metal. So a silver ion will pull the electron through that wire and then gain it to become solid silver. Meanwhile, a solid copper ion that's present on that strip of metal copper is going to lose the electron and turn into ionic copper and dissolve into solution. As the reaction continues, just like before, we will have silver building up on this electrode over here, and then the copper metal will dissolve and slowly disappear over time. The side or the chemical that's gaining those electrons is the cathode, and the side that loses electrons we call the anode. On the anode side, since we're losing electrons, we're gradually becoming more positive, which is especially easy to see here because you can see that the copper ions will start to accumulate in solution. And then on the cathode side, since it's gaining those electrons, it's going to be getting more negative, which is easy to see here because we'll be losing positive silver ions. And that brings us to the salt bridge, and the salt bridge contains ions which are going to dissolve into either the anode or the cathode to help offset that change of charge. Since we're getting more positive at the anode, the negative ions, which is chloride in this situation, will dissolve into that solution. And then the positive ions, which is sodium in this case, will dissolve into the cathode solution. And now we need to address the equation that we have on the right side, which is used to calculate E cell. As the electrons move from anode to cathode, you can measure the electric potential that they have. And that's a concept that is more physics-based, but here we can just think of it as how much do they want to go to the cathode. That value can be calculated with this equation here, which is an extremely important high-yield equation. And what this equation does is it takes the reduction potential at the anode and subtracts it from the reduction potential of the cathode. There's the reduction potential for copper, and there's the reduction potential for silver. We can plug those values into that equation to calculate the total potential for this cell, which again is basically just telling us how much do these electrons want to move to the cathode. And just make sure that you do understand that these values are calculated at standard conditions, which means this equation also only applies to standard conditions. So finally, to calculate the E cell for this galvanic cell, we do E cell equals 0.80 because silver is at the cathode, minus 0.34 because copper is at the anode, to give us a final value of 0.46. And a lot of people get really confused as to why we don't flip the sign for 0.34 since the reaction is actually proceeding in the opposite direction. And the reason for that is because that 0.34 also tells us how much the solid copper want to hold on to its electrons. So what we're basically saying is that silver ions want to gain electrons with a value of 0.8, and solid copper is resisting that movement of electrons with a value of 0.34. And finally, you want to be able to connect the E cell to delta G. And luckily, that's a really simple equation. It is just delta G is equal to negative NFE, and N is the number of electrons in the balanced redox reaction between the two species involved. F is Faraday's constant, which they will usually just give you in the question, and then E is the E cell that you calculate from the equation above. And notice that if you have a positive E, you end up with a negative delta G. So a positive E cell indicates that this is a spontaneous reaction. And in order to be considered a galvanic cell, the reaction does have to be spontaneous, so E cell does have to be positive.